when you have two vectors, we often label them with lowercase letters. They have magnitude and they have direction. But what they don't have is like an absolute location. So like if here's vector u, whether it's here or if I move it and it's over here, it's still like the same vector u, because they both have, these two vectors are totally equivalent. They have the same magnitude and the same direction. And when you add two vectors, we saw in the most recent lesson that you can add vectors by putting them like this so they have the same, what's called initial point. And then if you were to make a parallelogram, the diagonal of that parallelogram would be the sum of the two vectors. Now, an alternate way besides the parallelogram, if I have my u and I have my v, let's just draw them out like that. You could also do u plus v by doing something called the head-to-tail method, where you take the u and you put the tail of v onto the head of u like that. And then if I make a vector from the tail of the first one to the head of the second one, I get the same thing, u plus v. Notice how that's the same thing you get in this parallelogram. And you could also, it doesn't matter which direction you use, if you take v and you put the tail of u onto the head of v, and then you make a vector from the tail of the first one to the head of the second one. So you could, this is also, I'll just write v plus u, although it's the same thing. It's the same thing. So whether you do a parallelogram or a triangle, it gets you the same resultant. If you add a vector plus itself, u plus u, that's like multiplication. It's 3u. And if I put them on, if I do tail to head method, it looks like that. Well, when this happens, when you talk about 3u, it's called scalar multiplication. And what happens is that the new vector will have the same direction as the original, the u, but it will be 3 times, the magnitude will be triple. So the length of this sort of line segment will be triple it. And that's called scalar multiplication. The next thing I want to show you is subtraction. Here's, let's say here's u, and here's v. The way you can do subtraction is you could put u and v with the same initial point, and in the opposite direction of v is negative v. It's kind of like scalar multiplication, but if I multiply by -1, I get in the opposite direction. So u minus v is the same thing as u plus -v. So if I make this parallelogram with u and -v, then this here, this red one, will be u minus v. That's one way to get u minus v, but I want you to see that also I could also slide this red one over to over here. That would also be u minus v. And in general, if I have two vectors, u and v, set up like this, if I just make the third side of this sort of triangle, if I put the arrow pointing towards the head of u, this will be u minus v. You can kind of see over here that this is also saying that v plus u minus v, head to tail, gets me u. But this picture is a little confusing. A lot of people want to put the arrow in the other direction. If instead I wanted to do v minus u, I would just draw this again, but this time for v minus u, I would put the arrow going in this direction. So that could be a little bit confusing. It comes up on the SAT 2 sometimes. So to summarize, u, v, u plus v, u, v. If I draw that in, if I wanted to make it u, if I want to make it u minus v, I just point towards the u. If I want to make it v minus u, I point it towards the v. In math, sometimes we take a number like 10 and we split it up into like the sum of two other numbers. We can do the same thing with a vector. Here's a vector whose magnitude is 10 and whose direction I'm going to make with respect to the horizontal 36.9 degrees. This, to find out what is this 10, like what it's the sum of two vectors, and just like the number 10 can be written in a lot of different ways, the vector that has magnitude 10 and has this direction 36.9 degrees, it can be written as the sum of a lot of different things. Geometrically, it's the diagonal of a lot of parallelograms. Well, the simplest parallelogram is a rectangle. So I can say that the two vectors are this blue one and this red one. And those vectors are perpendicular. Well, we need to know, we know the direction of those vectors. One is pointing straight up, the other one's pointing to the right, but we don't know the magnitude of those two vectors. Well, we can use trigonometry for the magnitude, because in this right triangle, the 10 is the hypotenuse, so the adjacent side will be 10 cosine 36.9, which is actually equal to about 8. And this other one, the blue one, is 10 sine 36.9, which is about 6. Now, when you take a vector and break it up into its vertical and horizontal components like this, we could write this vector, which I'll just call u, this initial one, this diagonal one. We can write it like this. These two numbers, the 6 and the 8, go inside the parentheses. The 8 goes inside this angled bracket thing. This is a way to describe the vector. It's called the component form. And if I know that the component form is 8, 6, I can actually draw a picture of the vector by making a vector with magnitude 8 going to the right and one with 6 going up. If I put these things on a coordinate axis with 0, 0 as the sort of initial point there, then the coordinates of the terminal point of the vector will be 8, 6. But the vector itself in its component form is 8, 6. So this is, component form is when you split it up into its horizontal and vertical components. Now, a vector doesn't officially have a position, it just has magnitude and direction. So if I have a coordinate axis and I actually tell you the xy, this is like xy coordinates, not with the angled braces with the component form. So I can actually get the component form from here. One way is to get this point, which is 13, 1. And if I just basically subtract 13 minus 5, I get 8, and 7 minus 1, I get 6. So I can see that u is 8, 6. So we can actually calculate out the component form that way. This vector, which I'm describing now with sort of coordinates of the initial and the terminal point, we can get the magnitude, and the magnitude, sometimes they write it like absolute value, sometimes they have like this sort of like double looking absolute value. the magnitude you could get with the Pythagorean theorem. This is 8, this is 6, so this is 10. And in general, if I have it in component form, 8, 6, then the magnitude is going to be the square root of, if the component form is a comma b, it's going to be the square root of a squared plus b squared, which in this case is the square root of 8 squared plus 6 squared equals 10. This is easiest to do if the vector's initial point is at the origin and we have the coordinates of the terminal point. In that case, the 8, 6 is also going to end up being what the component form is. We could also get the direction in component form. If the vector is given in component form, we can get the direction by making this right triangle and doing tan inverse, in this case, of 8 over 6. Actually, I think that should be 6 over 8. Opposite over adjacent. That's 36.9 degrees. So that's the direction of it, at least with respect to this horizontal line. Now we can combine vectors mathematically speaking. If we have the vector defined in component form, we could, if I want to know u plus v, yes, I could try to draw this out. Draw out u, put them both at 0, 0 as the initial point. So 2 minus 3 is kind of down here, and minus 1, 2, and I can make this parallelogram and all. But it's even easier to add them, because you can just add together the horizontal component. 2 plus negative 1 is 1. And you could add together the vertical components, which are minus 3 plus 2, which is negative 1. So we can add without having to visualize it. We could also do like scalar multiplication with a sort of distributive property type thing for negative 6. And I could even do something like 2u minus 3v. I would get 4 comma negative 6. And then minus 3, the v is minus 1, 2. And essentially it's like doing the distributive property. We end up with 7 minus 12. So we can actually do arithmetic with these even without trying to visualize them. A unit vector, if I have a vector, in this case 8 comma 6, a unit vector is a vector that has the same direction but whose magnitude is just 1. So the magnitude of this vector is 10 that we saw before. So the trick is that you take u and you divide it by its own magnitude. So we get 8 comma 6 divided by 10. And now we get 0.8 comma 0.6. And what that is this tiny unit vector. It's in the same direction, but its magnitude is just 1. We could also turn that into 3/4. 4/5 and 3/5. Now there are two vectors that are very famous that we give names to. One of them is the vector 0, 1, which is this little 1. It's a unit vector, and it's pointing sort of straight up. We call that j. And another important vector is the one that could be described as 1, 0. It's pointing to the right. It's got a magnitude of 1. We call that I. This isn't the same I as the imaginary number I. Well, we can take any vector like 8 comma 6, and we could split it up into 8 comma 0 plus 0 comma 6. And each of those are multiples. In this case, this is the same thing as 8 times 1, 0. And I can sort of, it's kind of like factoring out the 6, 0, 1, which becomes, over here, it becomes 8I plus 6J. And that's called decomposing the vector into what's called a linear combination of I and J. So you get some kind of vector, like 8, 6, and if they want you to write it as like I's and J's added together, that's the way you do that. Now, here's a interesting question. I have a vector with magnitude 13, another one with magnitude 10, and the angle in between is 30.5 degrees. And in the last lesson we saw that we could find out the resultant vector, but it's pretty annoying and complicated by drawing a parallelogram and by making this and using the law of cosines. We need to get this angle over here, then the law of cosines to get this, then we can get this angle here, and it's a lengthy process. But using vector arithmetic that we've done just now, we'll be able to do this question easier. So this question, the way they would word it though, is instead of giving us these three pieces of information, they would instead just tell us the vectors in component form. So I'll call this V, and it's, let's say I told you that it was 5, 12, and this is U, and I told you that it was 8, 6. And now that's the information we have. So this is similar to yesterday, where we were given the magnitudes of the vectors and some stuff about the angle between them. Here I'm just telling you the component form of each of the vectors. So now U plus V is very simple. We just add the first component, which is 13, and the other one is 18. Now the magnitude of U plus V is going to be the square root of 13 squared plus 18 squared, which is 22.2, which is the same answer we would get if we did this question, where this was 13, and this was 10, and this angle was 30.5, and we were finding the resultant, the magnitude. So that's a lot faster than doing all that sort of law of cosine stuff. And as far as the angle, here's the resultant here. And we want to know this angle also. Well, we can calculate that angle by imagining this horizontal and by subtracting this angle minus this blue angle. Well, the red angle is tan inverse of 18 over 13. Whereas, this is the blue angle is what we want. We'll subtract the red minus the green. The green angle is tan inverse 6 over 8. And that becomes 54.16 minus 36.87, which is 17.3 degrees. And those are the same answers you would get if you took the same question and phrased it this way: 13, 10, 30.5 degrees. So those are two questions phrased in different ways, and one of them required law of cosines, law of sines. The other one just required this vector arithmetic.